Okay, so hello and welcome back. This is exercise 1.4. So let's see what we have here. We have some exercises, around 13 of them, or exactly 13 of them. So let's start with the first exercise. And you want to basically, this is exercise 1.4, and exercise number 1, you want to determine whether or not each of the definition of star given below gives a binary operation. In the event that star is not a binary operation, gives justification for this. So you want to know whether basically star is a binary operation in each of the cases below. Now, part one of this question is on Z plus defined by star, or basically defined star by A star B is equal to A minus B. A star B is equal to A minus B. Now Z plus is the I suppose Z plus is the well, there is no way to know what Z plus actually is, so we need to go and take a look at the definition of Z plus. Well, I suppose there is no good way to check whether basically what Z plus is. There is one way to check that, so let me I know a part of this text, which is one of the other chapters that we have done before. Let me take a look at that chapter and I'll tell you what Z plus is actually. Well, you know that basically there is a problem in mathematics, and these types of definitions are different across different types of texts, meaning that whatever sort of text that you're using, you need to know basically the types of agreements that have been put in place for that particular text. Now, since I have read this text before, there is a chapter on basically in class 11, the first chapter in class 11, which is about sets. And somewhere in the beginning of that text, it's been given that, for example, Z plus written this way, and not, for example, Z plus this way, or Z plus this way, or Z plus this way, because these could have completely different meanings, right? Even in the same text, basically. So Z plus written this way, meaning that not as a subscript, but plus as a superscript on the right hand side of Z, that means, for example, the set of positive integers. The set of positive integers. And there is and in the same text, the other sort of, well, agreement that I have come across is that if you write, for example, Z star, what that means, at least in this text, is the set of non-negative integers. the set of non-negative integers. So the set of non-negative integers would be basically z star, which is as a set basically 0, 1, 2, 3, and so on and so forth. That is the set of non-negative integers, which includes 0 as well. Now the set of positive integers, z plus, is basically 1, 2, 3, 4, and so on and so forth, all the way up to infinity, which is the same thing as the set of natural numbers, right? So you need to be careful about that when they say that z plus, you need to know exactly what is meant by that. Although, of course, I mean, otherwise you could make mistakes, of course. And or probably you don't even know what to assume, what not to assume, right? So, or basically in the same text, when we say that, for example, q, when we say that q plus, what that means that q is a set of rational numbers, and so q plus would be the set of positive rational numbers, and when you say that, for example, r plus, what that means is that the set of positive real numbers. And so on and so forth, right? So when you say the set of, for example, positive integers, what that means is that 1, 2, 3, 4, and so on and so forth, of course not including 0. If 0 is supposed to be a part of an element of that set, then they use z star, z subscript star, which means that the set of non-negative integers, which means that 0 is also there. So you need to of course understand that. So having that out of the way, that z plus is the set of positive integers, and so z plus is equal to basically the set containing 1, 2, 3, and so on and so forth, the same as the set of natural numbers. We define star by a star b is equal to a minus b, and of course we had a definition over here, and I guess I need to write these definitions somewhere so that we can have them all in one place. So let me actually do that right now. That would be a review of all of the definitions that we had in all of the previous 4 videos, and also then we will have all of these definitions in one place. We will be able to actually use them somewhere. So let me write down these definitions on another layer. 215 on another layer here. So all of the definitions related to this, not here actually, but all of the definitions related to this section. Oops, no, I didn't mean to go over here. Okay, so from the very beginning of binary operations, we had definition number 10. We had definition number 10, which was a binary operation star on a set A, a binary operation star on a set A is a function is a function star a times a, or the Cartesian product of a to a, and we denote the star of a comma b as by a star b. So that was definition number 10. Then we had the definition number 11. Then we had the definition number 11, which was basically a binary operation on the set X is called commutative. A binary operation on a set X is called commutative. If a star b is equal to b star a for every a and b belonging to X. So this was another definition about basically being a binary operation being commutative. We had another definition number 12. We had definition number 12, which was basically a binary operation star on a set A, a binary operation star on a set A is said to be associative if a star b star c is equal to a star b star c for every a, b, and c belonging to A. And that was basically definition number 12, which was about a binary operation being associative. Then we have another definition. This was definition number 12. So we have definition number 13. We have definition number 13, which is given a binary operation star on A, given a binary operation star on A, an element E belonging to A, if it exists, is called identity for the operation star, is called identity for operation star if A star E is equal to A is equal to E star A for all A belonging to A. For all A belonging to A. So that was the definition number 13. We had definition number 14. We had the definition number 14, which was, let me underline these. Definition number 14, which was given a binary operation star on A, given a binary operation on operation star on A, operation star on A, with the identity element E in A, with the identity element E in A, an element E belonging to A is said to be invertible. An element A belonging to A is said to be invertible. With respect to the operation star, with respect to the operation star, if there exists an element B in A, if there exists an element B in A such that A star B is equal to E is equal to B star A, and B is called the inverse of A. B is called the inverse of A. Sorry, not A, not uppercase A, of course. B is called the inverse of A and is denoted by A inverse. Right, so that was definition number 14. And that was basically all that we had here. So now what I'm going to do is that I'm going to just simply make a screenshot here so that we have access to these definitions anytime that we need them. Okay. I'm going to save this somewhere on desktop, for example. Binary operation definitions, and call it on desktop somewhere over here, and then forget all about it. Okay, and then I'm going to now go back to here, and then we will continue with what we were doing. Okay, and then basically the definitions are going to be found hopefully somewhere on desktop, because I put them there. Okay, great. So basically then here is our definitions, everything that we had, 10 through 14. So now we can see what we had here. So exercise 1.4, we said that we want to know whether star is a binary operation in each of the following cases. And part 1 of this question was on Z plus, which is basically the same thing as natural numbers. Define star by A times A star B is equal to A minus B, which is of course not a binary operation, because suppose that I take, for example, 2 elements from here. I take, for example, so if you have this operation on the set Z plus, you have to define it like this: star as a binary operation on the set Z plus, which would be the Cartesian product of Z plus and Z plus 2 Z plus. And to make it more simpler, we can just simply write this as star as a binary operation from n on n, basically, because they are the same sets, basically, right? It's basically the same thing, the same meaning. Now, basically the Cartesian product of Z plus and Z plus is going to be, for example, all of these elements, like, for example, 1, 2, 1, 3, 1, 4, 2, 5, 10, 15, 10,000, 15 million, and so on and so forth. And then once that, basically, when you do when you perform the star of that A comma B, you will get basically basically what you will get is basically A star B. You will get A star B, which in this case happens to be A minus B, right? So A minus B in this case, so suppose that, for example, I take, for example, 1, 1. 1, so 1, 1 in this case, 1 minus 1 is equal to 0, which does not belong to the set of positive integers. Therefore, you can say that star is not a binary operation. Therefore, you can say that star is not a binary operation on the set of positive integers, or you can say that basically addition, or not addition, but subtraction. You cannot say subtraction, because subtraction doesn't make much sense. You have to say what you are subtracting from what. A minus B would be different from B minus A. So then, based on this, you can say that star is not a binary operation on Z plus, right? Now as the solution, what I'm doing here is that while we are going through these exercises, of course hopefully in the case of all of the exercises, I can solve the problem. If I can't, I will take a look at the solution and solve, and once I've understood the solution, then I will solve the problem for you. Now, if I don't have to consult the solution in order to solve the problem, even in that case, I will take a look at the solution, because sometimes most of the time you learn something new, or at least a different way of solving the problem when you take a look at the solution. So I think you should do the same thing if you are doing anything in mathematics, first of course you solve all of the problems on your own. If you can't, then of course then you will take a look at the solution, but then there is this problem, you need to know actually when and where to look at the solution and when not. So that's some sort of like something like an art, but then hopefully your problems will take care of themselves, or you will take care of your problems properly. Now over here we have on z plus star is defined by a star b is equal to a minus b. So the solution here, based on the solutions, the solution tells me that on z plus star is defined by a star b is equal to a minus b. A star b is equal to a minus b. It is not a binary operation. It's not a binary operation. As the image of 1, 2, as the image of, for example, 1, 2, and they're using 1, 2 as a counter example. The counter example that we used here was 1, 1. You can use any counter example as long as it works in your particular case. So as the image of 1, 2, so that would be 1 minus 2. As the image of 1, 2 under star is 1 star 2, which is equal to 1 minus 2, which is equal to negative 1, which does not belong to z plus. And that is basically the reasoning. So you can see that this is a very elegant way of stating the solution, of course, provided that you understand everything. So my way of solving the problem is rather informal, because I'm tackling the problem without knowing what to do. I have to go step by step. But then I suppose these guys, what they're doing, these people, what they're doing, they of course they have ample time to write down basically their solution, and then after that they will rewrite the solution in such a way that it becomes an elegant way of stating what I had to say, using many more different steps. But well, the way that I tackle the problem is different, because in the beginning I don't really know what the answer is. I have to go step by step and take as many logical steps to basically arrive at the solution. That's basically how anybody could solve a problem, provided that they didn't know what the answer was, right? So that is basically one thing. That's part one of this question.